Welcome to this series of videos where we're going to look at the higher tier only section of the Combined Science Physics GCSE course in the magnetism topic. And this focuses on something called the motor effect, and this is going to be a series of 4 short videos where we look into this in a bit more detail. So in this first video we're just going to go through the principles of the motor effect, and we need to start off by doing a recap of some information that you should hopefully know already, which is that when a current flows through a wire or through a conductor, a magnetic field is formed around the wire or around the conductor. Now you will probably have seen pictures like this before, but just to remind you, if this is the current flowing here from positive to negative, as always, the current is flowing here and our magnetic field is formed around the wire. You can see this here as circles. And you might have seen the right-hand grip rule, which is a way you can remember the direction that these circles, this circular magnetic field, is formed. The diagram on the right shows exactly the same thing, but using iron filings, and you can see the iron filings have arranged themselves into circles, showing that circular magnetic field around the wire. Now, what we're thinking about with the motor effect is what happens when we put this wire into another magnetic field. Because if we put this wire into another magnetic field, for example, between the poles of a permanent magnet, the wire will experience a force because we then have 2 magnetic fields. We have the permanent one, for example, the permanent magnet, and we have the magnetic field around the wire. And when 2 magnetic fields interact with each other, a force will be exerted. Just like if you put 2 permanent magnets close to each other, they will repel or attract depending on which poles you have close to each other. Let's look at a little diagram that hopefully will make that a little bit clearer. Here we have a simple circuit, okay, and you can see the battery. Again, the current will flow from positive to negative along the wire here, and then down through this conductor or wire, through a magnetic field, and we'll come back to that in a minute, and back round to the battery. We can also see then drawn on here the magnetic field of this permanent magnet going from north to south, from left to right. So we've got a current flowing down through this wire, we've got a magnetic field from left to right, and that means that this wire will experience a force, and it's labelled on here, and the direction of that force is going to be outwards. Now we'll look more at predicting the direction of the force in the second video, but for now we just need to understand that there will be a force on the wire because of the interaction of the 2 magnetic fields, the permanent magnetic field from the magnets and the magnetic field from around this wire. So we're going to have a think then about 3 key questions. If you'd like to pause the video here to have a go at answering the questions, then please do so. Otherwise, I'm just going to go through the answers now. So first of all, how we could increase the size of the force on the wire. Now there are 3 ways that we could do that. The first thing we could do would be just to increase the size of the current. If we have a higher current, then there'll be a stronger magnetic field around the wire, and therefore we get a stronger force. We could use a stronger magnetic field. By this magnetic field, I mean the permanent magnetic field, the permanent magnet. Be careful with your wording here. Don't just say use a bigger magnet. You can say a stronger magnet, but don't say a bigger magnet, because some very big magnets are actually really weak and some very small magnets are really strong. So use the term a stronger magnetic field. And finally, we could use a longer length of wire in the field. Now that's quite hard to achieve because normally the magnets are of a fixed size, but if you did loop the wire round so it's going through the magnetic field a number of times, for example into a coil of wire, then you could also get a stronger force, a higher force. Obviously, if you wanted to decrease the size of the force, you would do the opposite. You would decrease the current, use a weaker magnetic field, or use a shorter length of wire in the field. The next question then, how could you reverse the direction of the force? Well, there are 2 ways we could do this. We could reverse the direction of the current. So for example, if we swap the two connections on the battery round, so the current is now flowing up through the wire, through the magnetic field, we would get a force in the opposite direction. Or we could reverse the direction of the magnetic field. And again, don't just say things like change the poles. Be very clear that you are reversing the direction of the magnetic field. Now let's actually have a look at this on a demonstration. What you can see now is a setup on the screen which is going to show the motor effect when I play the video. We have a power supply here on the right, and the current is flowing down the red wire. It's flowing along this copper bar. It's then flowing away from us along this copper bar here, which is free to move, back down the back copper bar, through the black wire, back into the power supply. And so when we switch on the current, in this case, we are expecting to see a force on the wire here in the magnetic field. So the wire in this case is this copper bar that's free to move. We should see a force exerted on the copper bar. Okay, let's play the clip and see what happens. We saw there was a force to the left. So now to check what we've just predicted in terms of the reversing of various different quantities, what we're now going to do is replace the bar, but also to reverse the direction of the current by swapping the terminals on the power supply. And now there is a force to the right, as we would expect. Now what we're going to do is reverse the direction of the magnetic field by turning the magnet over, replace the bar, and we now see a force once again to the left. Finally, if we now reverse the direction of the current again, we should now see a force to the right. Let's go back then to our final question. Our final question was, what about if the wire was parallel to the magnetic field? Now this would be quite hard to achieve, but I mean if this wire, instead of going vertically down through the magnetic field, actually was going along in the same direction as the magnetic field. And the answer actually is that no force would be experienced. So if you want to experience a force, you need a situation where the magnetic field, here from north to south, and the current are at 90 degrees to each other. And the force that the wire experiences will then be at 90 degrees to both the current and the magnetic field. But that is the focus of the next video. So I hope that gives you a good idea of the basic concept of the motor effect, and in the next video we're going to look at something called Fleming's left-hand rule, which is what we use to predict direction of the force.